All right, today we are going to fill in some gaps on various topics, kind of based on what we've seen with previous assessments. So we have some extra time before we get into our unit by unit review, which starts tomorrow. We're just going to take today to kind of breathe, fill in some touch up info. So, a few different topics dealing with function representations first, then complicated factors, and then rate problems. And after that, if you missed class, kind of go into a free work mode today. So starting off with different function representations. So over here on the left of your note sheet, you'll kind of notice that, hey, we got different forms of equations. There's equations, there's graphs, there's tables. If we get it in equation form, we should just simply graph it in Desmos. If we're given something in table form, we're going to have to go through a little more longer of a process, but easy enough to see what our function looks like. So if we're asked in example 1, this question, if f of x is graphed below and g of x is this equation, then what is the difference in the y-intercepts of f and g? Well, it's really easy to see the y-intercept of f because that is just shown on our graph here, right? Our y-intercept is 2. But maybe not as clear cut to see with g. You might be able to tell from the equation that it should be -4. But let's go ahead and just confirm this with our graph here. So I'm in equation form, I type it into Desmos. My g of x is equal to 3x to the 4th power plus x to the 3rd power minus 4. And if I look here, my y-intercept is -4. So I'm going to kind of just notate that here with my g of x. So y-intercept of g, ooh, my writing's really bad today, is -4. So if I want to find the difference in those, the difference is going to be 6. So we have 2 minus a -4 equals 6. And we could even say more specifically, y int of f is 6 above g. So in example 2, we're given another equation for f, but this time we're given g in table form. So we can still compare these two functions. And in this case, we're asked to compare these maximum values. So that's super tough to see directly from the equation. Let's throw it into Desmos, see what's up. So first thing I'm going to do, I'm going to type this f in here. So delete my old graph, got f of x, that equals that -2. I think it was x minus 1 to the 2nd power. And I'm just going to double check, make sure I typed that in correctly. -2 times x minus 1 to the 2nd power. Cool. Then we're given g in the form of a table. So here's kind of our steps to make sure we get a nice table graph. Some of you know this already. Others, I think this might be the first time. In my new row, I'm going to click on the plus sign. I'm going to add a table. And we can change the names if we want, or we can leave it blank. I'm going to change the names to x and g of x. Shouldn't really matter. And I'm going to go ahead and type my x values in first. That's the -2, -1, 0, 1, and 2. -2, -1, 0, 1, and 2. And next, I'm going to type my g of x values, -6, 3, 6. Oh, oops, we actually just need to leave this as a y. Oh, we could say it as g, just not g of x. My apologies. So let's go back and just type in -6, 3, 6, 3, and -6. Now, might be difficult to see with just our dots what's going on. Maybe you can figure out what that max value is. What I like to do, though, is I like to turn on the lines so we can kind of see the trend of this graph. So if I click and hold this dot here, I can turn on these lines. I can also change the color if I want to. I'm going to change it to orange to make it pop a little more. Make my text a little bit bigger. And if we're comparing our maximum values, it looks like G has a maximum value of 6. F has a maximum value of 0. Notice how the Y value is 0. So we can kind of notate this real quick. G max is 6. F max is 0. So I'm going to say that the max of G, that's a G there, is 6 above F. Okay, last thing in our different representations, we've seen this before with function transformations, and I want to just kind of highlight it in case you missed that lesson or you're struggling with it. Sometimes we can write functions as transformations of other functions, and the best way to see this is through an example. So if we start with this f of x here, and say that f of x is equal to this formula, all right? And I'm going to start by just typing that formula in. Let me delete my old stuff. We have f of x equals, and it's 2 times 5 to the x power. Okay, there's my original function. Both g of x and p of x can be written as a transformation of that function. So if I type in a here, this g of x exactly as it's shown, g of x equals f of x minus 2. Notice how when I typed in f of x, it just gave me the exact same graph. Okay, if we're saying g is equal to f, that makes sense. And if I do minus 2, okay, it's taking whatever f was and it's shifting it down 2 units. We can look and see, hey, my y-intercept of blue is at 0, 2. My y-intercept of green is at 0, 0. We've gone down 2 units. So if I want to describe this, g is 2 units down from f. Similarly, we could check out what p is. Okay, so I'm going to kind of turn off g real quick and type in p. And this is f of x, I believe, plus 4. And notice how that plus 4 is inside of our parentheses in our problem. And if we look here, now we're comparing purple to blue. I'm going to kind of mark this y-intercept point. I'm going to count over, see where I hit that on my purple graph. It looks like I go 1, 2, 3, 4 steps. So I can say that P is 4 left of F. And we probably want to say 4 units, my bad, 4 units left of F, depending on our units on our graph. All right, moving on to the next topic. This is finding zeros with difficult factors. So a little bit of review, a little bit of extension. So in example 4, we can find the zeros of this factor form equation pretty quickly. We do that by setting each factor to 0 and solving. So I have 3 factors here. I have this x, I have this x minus 5, and I have this x plus 3. And our zeros are just going to be found by taking each of these and setting them equal to 0. I'm going to start with this one, x plus 3. If I set that equal to 0, then I could subtract from 3 on both sides, get x alone, x equals 3 for one of our zeros. Okay. Same thing can happen with this orange one, x minus 5. We set that equal to 0. We can add 5 to both sides. And that just gives us x equals positive 5. Lastly, if I take this factor out in front and I set that equal to 0, it's as simple as, hey, we have a 0 at x equals 0 here. So these are our 3 zeros of this factored form equation. We set each factor equal to 0, and we solve for the value of x. Now, we can do the same exact thing. Well, actually, before we move on, let me just throw this in Desmos real quick, show that this is what's up. So f of x equals x times x minus 5 times x plus 3. Boom, we have a 0 at negative 3, 0, and positive 5. That lines up with what we got from our work. Now, we can do the same exact thing for more difficult factors. Notice how in example 5, we have a pretty easy factor, this x minus 2, but now we don't have that same format for this 2x minus 3 here. So I can go through that same process with this x minus 2 first. X minus 2 equals 0. So I add 2 to both sides. I get x equals positive 2 as one of my factors. If I do this for this red factor, 2x minus 3, and set that equal to 0, we just have to take a few more steps. So I add 3 to both sides, add 3 to both sides. I get 2x equals 3. And then I can divide 2 from both sides here and get x over 3 halves, or x equals 1.5. Let's check that out, see if that lines up. So I'm going to kind of go with my f of x equals x minus 2 times 2x minus 3. And let me just double check I typed that in correctly. We can see, hey, I got to zoom in a little bit, but we have a 0 at 1.5, and we have a 0 at 2. So hopefully you can try this by yourself here, but we should have 3 zeros for example 6. We have this x out in front. That is going to give me a 0 at x equals 0. I have this middle factor, 4x plus 3. I'm going to set that equal to 0. Okay, I can subtract 3 both sides, get 4x equals negative 3, divide 4 both sides, get x equals negative 3/4. And the last one here is setting 4x minus 3 equal to 0. You can move similar steps here, just adding 3 to both sides. First, 4x equals positive 3. And if I divide by 4 both sides, I get x equals 3/4. And if you want to write these in decimal formats, you can too. X equals 0.75 would work. And with orange, it'd be x equals negative 0.75. So I just want a graph to check it real quick. We have x and 4x plus 3, 4x minus 3. Double check, make sure I did that right. 4x plus 3, 4x minus 3. So we have a negative 0.5, a 0, and a positive 0.75. All right, last fill in the blank that we're going to hit today deals with rate problems. And we kind of skipped this when we did our rational expressions unit, but this is something that can be handled with rational expressions. So let's read this problem first. Martha can paint a room in 2 hours. Jamie can paint the same room in 6 hours. How long to the nearest tenth of an hour will it take them to paint the room together? This is a question I pulled straight from an old EOC exam, so it's important that we kind of know how we can set this up and how we can solve it. So the biggest mistake, this would be the wrong way to do it, would think that, hey, Martha takes 2 hours and Jamie takes 6 hours. And if I add those up, I can say, hey, it takes 8 hours for them to clean it. Well, that doesn't make any sense. They should move faster if they are working together. So really, this is a speed problem. So we have to think of this as the idea of it's going to take room per hour is the speed that we're working in here, okay? So if I want to find the room per hour for Martha, she can paint a room in 2 hours. So for Martha, she can do 1 room every 2 hours. For Jamie, they can paint that same room, so I'm going to throw Jamie. Can do 1 room every 6 hours. All right, now if they're adding, if they are painting the room together, we can simply add those two things up. So we have our Martha, which is 1/2, plus our Jamie, which is 1/6. And that is going to equal 1 room over however much time it takes to get that room. So x is going to be equal to our time together. Okay, Martha's speed plus Jamie's speed equals their speed together. Now, if we have this problem, we're just going to work on solving it graphically to make sure that we're practicing that skill as well. We have a left side of our equation, 1/2 plus 1/6. I'm going to throw that in there. F of x equals 1/2 plus 1/6. And my other function, g of x, is going to be equal to that right side of the equation, 1 over x. And if we look here, I'm not concerned about the left side of my graph because those are negative values. I only want to focus on the right side of my graph because we can't have negative time. It looks like it's going to take our x value of 1.5. So it is going to take 1.5 hours in order for them to paint the room together. And I'm going to say from graph. So last one, hopefully you can try to set this up on your own. This time we have 3 students, Simone, Jeffrey, and Enzo. They're washing cars. We have Simone's washing the car alone. It takes 40 minutes. Jeffrey washes the car alone. It takes 30 minutes. Enzo, 24 minutes to wash the car alone. So if we put them all together, how long should it take? We can kind of go through that same thing where Simone is going to be 40 minutes. We know Simone's speed is 1 over 40. They have 1 car every 40 minutes. And I'm going to make a quick note of that. We are doing cars per minute here. I know Jeffrey takes 30 minutes. So 1 over 30 for Jeffrey. And I know Enzo takes 24 minutes. So 1 over 24 for Enzo. And if we add all of these up, we are going to get 1 over, so 1 car over x minutes, where x is the time together. And I'm going to graph it again to solve this equation so I don't have to spend too much time on it. From our graph, we can find that x value or the time it takes for them to wash the car together. I'm just going to replace these formulas here. I have 1 over 40 plus 1 over 30 plus 1 over 25, I believe. Let me double check. 40, 30, 24. My apologies. So 1 over 24. And on the right side of my equation, I still just have that 1 over x. If I zoom back, again, I'm still just worried about our positive x values because we're dealing with positive time. If I click on one of these, I can help locate that intersection. It looks like we intersect at an x value of 10, which means that altogether it is going to take our students 10 minutes to wash that car together.